In this video, we're going to work through some of the problems from the homework covering section 6.5, which is logarithmic properties. Let's start with expanding the logarithm as much as possible. We want to use the properties of logs in order to write it as a sum, difference, or product of logs, and we want to preserve the order, by which I think they mean make sure that if it's written 2 times a times b, that you have the log of the 2 thing here, the log of the a thing here, and the log of the b thing there. When you have a product of logs, they can be split up into the sum of the logs. So this becomes, for example, the log of 2 with the base of 10, which is not written but is understood to be below and to the right if you write the word log but do not write a base, plus the log, again base 10, of a, plus the log, again base 10, but not written, of b. In that form, we have stretched it out as much as possible. Let's take a look at another example. In example 2, we again want to expand the logarithm as much as possible by rewriting as a sum, difference, or product of logs. In this case, we have division inside the argument to the natural log. When you have division in the argument, it becomes subtraction of the 2 factors within the fraction. The numerator becomes the positive and the denominator becomes the negative, because remember that natural logs represent powers, and negative powers put things in the denominator. Therefore, we can write this one as the natural log of 14 minus the natural log of 15. Let's take a look at the next example. In problem number 3, we again want to expand the logarithm as much as possible by rewriting as a sum, difference, or product of logs. In this case, we have the log of 1 in the numerator divided by 3 to the x. The first thing we do is we split up the fractional part by rewriting this as the log with the understood base of 10, which can be written but doesn't have to be, of 1, minus the factor coming from the denominator in log base 10 of 3 to the x. Now, if we want to split this out and make it as long as we possibly can, the next thing we can do is consider what the log base 10 of 1 is. This means 10 to some power equals the number 1. Remember that if you want to, you can go to the side and you can set your logarithm equal to a variable and then switch forms. This means 10 to some power equals 1. The power must be 0. Therefore, the log base 10 of 1, or writing it without the base, log of 1, that must be 0. We can replace this part then with a 0 so that we come up with 0 minus the log of 3 to the x power. Now, this is what the book wants written next. The other thing we can do, however, in order to continue expanding it, is remember that there is a property that says the power on an answer part can be brought to the front where you have multiplication of the powers. In other words, the log is one power and the x on the 3 is another power. This means that we can now rewrite this one by eliminating the 0 and writing negative x log of 3. This means log base 10 of 3 multiplied by negative x. This is as expanded as we possibly can. Let's take a look at the next problem. In problem number 4, we are to condense to a single logarithm if possible. In other words, we want to do the same thing we just did, but in reverse. First, we look for anything on the front of the natural log to push back inside as the power on the answer part. However, all of our coefficients on the left are positive 1, which makes the power on 7, x, and y all positive 1. Then we notice that we have addition of natural logs. They're all the same base, they're all base e. So this means that I must originally have had an answer part of a product of 7x and y. This then becomes the natural log of 7 times x times y, which can be written in a fully condensed form as the natural log of 7xy. It is not necessary to put the parentheses around the argument, but it is a good habit to get into. Let's take a look at the next problem, which is number 5. In number 5, we again want to condense to a single logarithm if possible. In this case, notice that we have only the coefficient 1 in front of log base b of 32 and a negative 1 in front of log base b of 8. The negative can be thought of as subtraction, and that would leave the coefficient to be a positive 1. We don't need to pull the power inside since 8 to the first is still 8 and 32 to the first is still 32. We have subtraction between two logs with an identical base of b. Therefore, we can combine them into the ratio of two values. This means that we're going to have the positive 1 becoming the numerator part of the answer part, with the 32 as the numerator of the answer part, and the 8 as the denominator of the answer part. That's because we originally had subtraction. Now we can reduce 32 divided by 8 to give us 4 to finally write our solution as the log base b of 4. This is a fully condensed form. Let's look at problem number 6. In problem number 6, we want to condense to a single logarithm if possible. We have a negative on the front, which can be thought of as a negative 1 power. This time I have no other terms, so I won't have a fraction or a product. I do then want to bring the negative inside as part of the power. I can then think of this as the log of the answer part, 1 over 10, being raised to the negative 1 power. This negative 1 was at the front, but was brought inside onto the answer part. What happens when you take a fraction to a negative 1 power? You're right, it turns it upside down. So this becomes the log with an understood base of 10 divided by 1, now raised to the first power. 10 divided by 1 is 10, and 10 to the first power is still 10. This gives us the log of 10. Now this is what the textbook is looking for, but be aware that this could be reduced even more. Since we have log and no base written, the base is understood to be 10. And that means I have log base 10 of 10 equal to some unknown value. This means 10 to some power equals 10. Well, what power would you raise 10 to get 10? You've got it. It's going to be x equal 1. In other words, this could have been reduced to the simple number 1 and not a logarithm at all. But again, our directions say to condense to a single logarithm, so we leave it in this form, though it is equivalent to the number 1. Let's take a look now at example number 7. In example number 7, we are told to expand the logarithm as much as possible. We want to rewrite as a sum, a difference, or a product of logs. We'll preserve the order from left to right, doing the numerator first and then the denominator. When you have multiple factors inside of the answer part, anything coming from the numerator will be positive, and anything coming from the denominator will be negative. In this particular case, the first thing we deal with is the fraction. We split it into the numerator and the denominator by writing the log of the answer part of the numerator, x to the 10th y squared, minus the log of the denominator, which is z to the 5th. Now I can apply the product rule to the first term since I have two factors inside the answer part of the first term. This will become the sum of two logs. This becomes the log of x to the 10th plus the log of y squared. The minus the log of z to the fifth simply tags along the back. If I'd had two factors in the denominator, they would both have been subtracted because they would both have been coming from the original denominator. The last thing that you can do is pull the power to the front. When you're condensing, it's the first thing you undo, and when you're expanding, it's the last thing you do. So now we pull the 10 to the front to get 10 times the log of x plus 2 times the log of y minus 5 times the log of z. Notice that the power that's at the front is the power that was sitting directly on that answer part and that answer part alone. We don't have a 2 in front of this one because 2 was sitting on y and not on x. This is fully expanded. Let's take a look now at problem number 8. In problem 8, we again want to expand the logarithm as much as possible. Rewrite as a sum, a difference, or a product of logs. Again, we'll preserve order from left to right, writing the numerator first and then the denominator. This time we do have two factors in the denominator. Again, we start by writing the natural log of the numerator, and then we're going to subtract the natural log of the denominator. This time we have two factors in the denominator, so we'll apply the product rule to the second term here. However, because they're both coming from the denominator, they must both stay negative. This gives us minus the natural log of y to the negative 3 and minus the natural log of z to the 8th. If you're confused by the signs, remember that you can think of this as having a negative being factored out, and then they would be a plus, which gives you the product rule that you're accustomed to seeing. In other words, the plus is hiding inside of the double negatives that you see here. The last rule we apply is to pull the power on the answer part to the front of the logarithm. This will give us negative 4 natural log of x minus a negative 3 times the natural log of y. Notice that the negative 3 and the negative are two separate negatives. That'll give us a double negative, which will make it a plus. On the last term, instead, we pull the 8 to the front, which is positive, and then it gets multiplied by the negative, which will leave it being negative. Our final result is going to be negative 4 natural log of x minus a negative 3, which gives us plus 3, the natural log of y, minus 8 times the natural log of z. This is the most expanded and simplified form that we have. Let's move on now to problem number 9. In problem 9, again, we want to expand the logarithm as much as possible. We want to rewrite as a sum, a difference, or product of logs. Again, we'll preserve order left to right, numerator to denominator. This time, inside the answer part, we have a radical, and under the radical, we have two factors, x cubed and y to the negative 8. First, we need to deal with the radical by rewriting it in power form. This gives us the log base b of the quantity x cubed times y to the negative 8 being raised to the 1/2 power. Remember that the 1/2 power represents the radical of square root. Now, how can I get to these guys right here? There are two ways of doing it. First, you could move the 1/2 to the front, and then you could split it into a product, or you could pull the power in on each of the answer parts. We'll take a look at both methods. Method 1, we pull the 1/2 to the front, and it gets multiplied by the logarithm base b of x cubed times y to the negative 8. Then we need to split up the product into a sum, but because we have a 1/2 as a factor on the front, the 1/2 gets multiplied by the product when it gets split into a sum. and this will lead us to this result right here. Notice that we then need to distribute the 1/2 across both terms so that we have 1/2 the log base b of x to the third plus 1/2 log base b of y to the -8. Our next step would be to pull the power on the answer part to the front and multiply it by the 1/2 that's already there. If we do that, this will give us 3/2 at the front of the first term times the log base b of x plus a -8 times 1/2 will give us a -4, so we end up with -4 times the log base b of y. This is the most expanded form that we have. Now let's take a look at doing it the second way, which is to pull the power in and apply it to each of these powers. Remember, when you have one base and two powers on it, you multiply the powers. Let's do this in a slightly different color so we don't mistake one method for the other. This will lead to the logarithm of base b of x to the 3/2 by multiplying the 3 times 1/2 times y to the -4 power by multiplying the -8 times 1/2. The next thing we need to do after that is to apply the product rule to split the product into the sum of two logarithms. This gives us the log base b of x to the 3/2 plus the log base b of y to the -4. Then we need to apply the rule that says pull the power to the front of the logarithm. This then gives us 3/2 the log base b of x minus 4 times the log base b of y. Notice that this method is shorter and has fewer steps, but leads to the same result we got before. You can choose which method you prefer. Problem number 10 is very similar to the last problem. We want to expand the logarithm as much as possible by rewriting as a sum, difference, or product of logs. In this case, we have multiple factors inside the answer part, and we have a radical, but the radical is not on all the factors. Notice that you can split the factors by putting multiplication between the x squared, the y to the 4th, and the radical itself. Under the radical, we have multiplication between the x squared and the y to the 4th. The next thing that we want to do is to expand this. We'll start by applying the property for splitting up products into sums. Since there's no base written, it must be base 10, which gives us log of x squared plus the log of y to the 4th plus the log of the square root of x squared y to the 4th. The next thing we can do is deal with the log of the square root of x squared y to the 4th by rewriting just that one term as that raised to the 1/2 power. Remember that when we have radicals, radicals are fractional exponents. And this becomes log of x squared plus log of y to the 4th plus the logarithm of, coming to the side, we can do our work here to see that we would have x squared plus y to the 4th rewritten as x squared plus, not plus, times, my bad, times y to the 4th being raised again to the 1/2 power. This gives us one base, x, with two powers, 2 and 1/2, and another base, y, with two powers of 4 and 1/2. Then we multiply the powers, and that gives us x to the first power and y to the second power. Then we can rewrite this answer part as xy squared. Now we need to deal with this product here inside this answer part by splitting it into the sum of two logarithms. The first two terms continue to follow until we're ready to apply that last property of pulling the power on the answer part to the front. This gives us the log of x plus the log of y squared. Finally, we're ready for the last property. Pull the power on the answer part to the front and write it as 2 times the logarithm base 10 of x plus 4 times the logarithm base 10 of y. There's no power here to bring to the front to the x other than 1, so it remains plus log of x. The last term becomes plus 2, the log of y. This is the most expanded form that we have for this particular problem. Let's move on now to problem number 11. In problem 11, we're asked to condense the expression to a single logarithm using the properties of logarithms. In other words, let's go the other direction. Notice that here we have the difference of 2 logs, which means that we have a fraction. The positive ones are in the numerator, the negative belong to the denominator. This then can be written as the log base b written one time only, with a numerator of 10a to the 9th power divided by 5a to the 4th power. That becomes the new answer part. Of course, you should reduce whenever you can, so 10 divided by 5 would give us a 2, and a to the 9th divided by a to the 4th gives us a to the 5th. That's using the exponent rule that when the bases are the same, both a, we subtract the powers. 9 minus 4 gives us a to the 5th. The most condensed form then is log base b of 2a to the 5th power. Let's look at problem number 12. In problem 12, again, we want to condense the expression to a single logarithm using the properties of logarithms. This time we have a positive term, 4 log of x, a negative term, minus 1/2 log of y, and another positive term, 4 log of z. Notice that these have coefficients other than a positive 1. So the first thing we need to do is push those coefficients back in as powers on the answer part. This becomes the log of x to the 4th. The next term becomes minus the log of y being raised to the 1/2 power. And the final term becomes plus the logarithm of z being raised to the 4th power. While the parentheses aren't strictly necessary, they are a good habit to get into. Remember that the 1/2 power also represents the square root, so we can write y to the 1/2 as the square root of y. Now that we have returned all of our coefficients to 1s, any positive term will become a factor in the numerator, and any negative will become a factor in the denominator. All 3 have to have the same base. Since it's not written, it's understood to be 10. Therefore, I have a factor of x to the 4th from the positive term here, and another factor of z to the 4th from the final factor. And then, in the denominator, I have a factor of y to the 1/2, or the square root of y, which goes in the denominator because it came from a negative. And again, while not strictly necessary, it's a good habit to put these into parentheses. This is the combined form and the most condensed form we have for that expression. Let's take a look now at problem number 13. In problem 13, we're to rewrite the expression as an equivalent ratio of logarithms using the indicated base. In other words, we want to convert the log base 9 of 19 to something with base 10. There's a rule for this coming out of the textbook. Let's write the rule and then apply it to this problem. This is called the change of base formula. The log base b of m is equal to the log base a of the original answer part, all divided by the log base a of b. This is not the power rule for logarithms, because we have 2 separate logs written and we're dividing the entire log. Notice that the original answer part goes in the numerator and the original base becomes the answer part of the 1 in the denominator. I keep it straight by remembering that the base goes in the bottom, double B. And now let's apply this to the log base 9 of 19. If I want to convert this to something expressed in terms of base 10, I can write this as log base 10, which does not have to be written, of the original answer part 19, divided by the log base 10 of the original base, which is 9. This is all that the textbook is looking for. The reason for doing this is that originally there were tables only for base 10 and base E, which is Euler's number. There were no other basic tables that existed. And those days, we had to convert everything to one of those two to be able to look them up in the table. It is still true that the vast majority of calculators only have base 10 and base E on them. This means that for most calculators, you still have to convert to use the calculator to find them. Some of the newer graphing calculators have the ability to handle any base, but that's not true of a scientific calculator. Let's take a look now at problem number 14. In problem 14, it says, suppose the log base 9 of 11 equals A, and the log base 9 of 10 equals B. Use the change of base formula along with properties of logarithms to rewrite each expression in terms of A and B. We have the log base 10 of 9, but up here we can see that this is written with the log base 9. How are we going to rewrite this? Let's rewrite our change of base formula again. Now that we have the change of base formula rewritten, let's see how we can use these expressions to rewrite this problem here. Since these are both 9 as the base, let's convert this log base 10 of 9 into a base of 9. That means that I can rewrite log base 10 of 9 as instead the log base 9 of 9, where 9 is the original answer part and 9 is the new base, divided by the log base 9 again of the original base, which was originally 10. Now, I know from what it has up here in the directions that the log base 9 of 10 is the value of B. This means that I can replace the denominator with B. What about the numerator? If we come to the side to do a little bit of work, remember that we can always set log base 9 of 9 equal to an x or some other variable so we have something to solve it with. This means that 9 to some unknown power equals 9. The power must be 1. Therefore, we can replace log base 9 of 9 with 1. The base and the answer part are powers of the same number, 9, and that gives us the power itself. 9 to the first gives me 9. This means that I can rewrite log base 10 of 9 as 1 divided by B. Let's take a look now at the next problem, which is problem number 15. Suppose the log base 11 of 5 is A and the log base 11 of 10 is B. Use the change of base formula along with properties of logarithms to rewrite each expression in terms of A and B. This time we have the log base 10 of 5 divided by 10. We could, if we wanted, simplify this before starting. Or we could simply convert it now into log base 11. If we convert to log base 11, we will have log base 11 of the original answer part, which is 5 divided by 10, all divided by the log base 11 of the original base, and the original base was 10. Looking up here at our expressions, I have that the log base 11 of 10 is equal to B. That means that I can replace the denominator again with B. What about the numerator? I need to come to the side to see if I can split this up somehow. Coming to the side to do some scratch work, I have log base 11 of the quotient 5 divided by 10. I don't want to reduce the 5 over 10 because my expressions have 5s and 10s in them. Otherwise, I would reduce it to 1/2. In this particular case, this can be split up using the quotient rule for logarithms, that when we have a ratio of factors in the answer part, it becomes the difference of the logarithms. The positive one is from the numerator, and the negative one is from the denominator. This gives me the log base 11 of 5 minus the log base 11 of 10. I know that the log base 11 of 10 is b. I saw that from the first part. And the log base 11 of 5, based on the directions to the problem, is equal to a. That means that my numerator is now a minus b divided by b. This can be written either in this form, combined together, or you can split it into two fractions by dividing each numerator by the common denominator of b. Since b divided by b is 1, this can be written also as a over b minus 1. On an exam, I would take either that solution or that solution there as your solution to this problem. Let's move on now to problem 16. This says, use properties of logarithms to evaluate without using a calculator. We have the log base 2 of 1 over 4 minus 4 log base 2 of 2. First, let's condense this logarithm into one logarithm. First, we'll take the 4 and push it back inside as a power on the 2 that's in the answer part. That means the first term just sort of hangs out and waits for me to be done. This gives me log base 2 of 1/4 minus log base 2 of 2 to the 4th. The next thing I can do, since I have the difference of two logs, is write them in fraction form. When I write them in fraction form, this means that the one that was positive becomes the numerator of the new answer part, and the one that was negative becomes the denominator of the new answer part. I know it's a complex fraction. Let's go to the side and see if we can simplify it. We have 1 over 4 divided by 2 to the 4th. 2 to the 4th can be thought of as 16. This is 1/4 divided by 16, which is the same as 1/4 times 1 over 16. This gives us the number 1 over 64. Now we can rewrite this as the logarithm base 2 of 1 divided by 64. If we want, we can write 64 as a power of 2. 64 is 2 to the 6th. This becomes 1 over 2 to the 6th. We can now write this as the logarithm base 2 of 1 over 2 to the 6th. If we could get the answer part written as 2 to a power, then the logarithm would become that power. Since it's in the denominator and I have 1 in the numerator, I can move the 2 to the 6th to the numerator by changing the sign of the exponent from positive 6 to negative 6. This gives me log base 2 of 2 to the negative 6. If you set this equal to some x, you're asking 2 to some power equals 2 to the negative 6. The answer should be negative 6. So the result for our entire problem is negative 6. Let's take a look now at problem 17. In problem 17, we want to again use properties of logarithms to evaluate without using a calculator. This time we have 3 times the log base 8 of 2 plus log base 8 of 64 divided by 3 log base 8 of 4. Notice that we have 2 factors that are outside the logarithm that need to be pulled inside before we can do anything else. First, I will rewrite this as the log base 8 of 2 to the third for the first term, plus the log base 8 of 64, all divided by the log base 8 of 4 to the third. The next thing I want to do is write what 2 to the third is and what 4 to the third is. When I do that step there, I get the log base 8 of 8, since 2 to the third is 8. For the second part, I get the log base 8 of 64 divided by the log base 8 of, 64, since 4 cubed is 64. Any expression divided by itself is equal to 1. On this first term, this says log base 8 of 8 has to equal some power. What power do we raise 8 to get 8? The answer is 1. This becomes then 1 plus 1, which gives us the value of 2 for our final answer. Let's take a look at the last problem in this homework section, problem number 18. Use the change of base formula to evaluate the expression as a quotient of natural or common logs. Use a calculator to approximate it to 4 decimal places. In this case, I typically use natural log. You can also use log base 10, which is the common log. Remember the change of base formula. Natural log of the answer part, which is 22, divided by the natural log of the original base, which is 5. Keep the base on the bottom. Now grab your calculator so that you can compute the natural log of 22 divided by the natural log of 5. When you enter it into the calculator, the natural log of 22 gives you approximately 3.091 ... The natural log of 5, on the other hand, is approximately 1.609 ... When we take the natural log of 22 and we divide by the natural log of 5, we end up with the value of approximately 1.9205726. This can be rounded to 4 decimal places by rounding to the 4th place, which is where the 5 is now. Since the next digit is a 7, we round up and this will become a 6. That gives us 1.9206 for the approximate value of the logarithm base 5 of 22. This is the end of this video covering section 6.5, applying logarithm properties. In the next video, we'll be looking at the next section, which is 6.6, solving exponential and logarithmic equations.